equivalence classes. Now, an equivalence class is a subset of the given set such that any two elements in it are equivalent to each other. So, equivalence class of A based on a relation R in A is represented as A by R. And if we are not talking of one equivalence class, but the set of all equivalence classes, then A by R is how it is represented. Now, it is read as A modulo R, set of all equivalence classes, or it is also referred to as or read as quotient set of A relative to R. Okay. Say for example, we have a set of all triangles in a plane. Let's say this is A, and R is equal to X is congruent to Y. X and Y belong to A. Now here equivalence class X, equivalence class can be written like this or like this, is the set of all triangles congruent to X, which means basically we can also say equivalence class Y within brackets is the set of all triangles congruent to Y. And this, some of the properties of equivalence classes would be, let's say we have a set or an equivalence relation in A, and let X and Y be arbitrary elements in A. Okay, in that case, remember X belongs to X. X belongs to class X, equivalence class X. If Y belongs to this class, then Y is equal to X. So within an equivalence class, we can pick any one element as the class name, okay? Because they are all equivalent to each other. Now, if so X, equivalence class X is equal to equivalence class Y implies or implied by X comma Y belongs to R if and only if, or rather this, if and only if X relates to Y. Okay, now keep the previous example while you are trying to understand these things. It will become easier. Okay, and either X equal to Y, or see, either they are equivalent, same equivalence class being referred to using two different elements, or the intersection of these two is a null set. So either the equivalence classes, two equivalent classes are either disjoint or they are identical. So that is equivalence classes. Now let's look at partition of a set. Okay, so let X be a non-empty set. A set P is equal to A, B, C of non-empty subsets of X will be a partition of X if, and two conditions have to be satisfied. One, A union B union C is equal to X. Okay, and second condition is the intersection of every pair of distinct subsets of X belonging to P is the null set. Don't look at this first. Subsets of X belonging to P. Okay, so let's say x is equal to 1 comma 2 comma 3 comma 4 and goes on up to 9 comma 10. Okay, and you can take this in any way you want. Make three subsets of this. Okay, so 1 4 9 is a subset. B is equal to 2 3 10 and C is equal to 5 6 7 and D is equal to 8. Okay, so these are the subsets of X. So A is a subset of X, B is a subset of X, C is a subset of X, and D is a subset of X. Okay, so P, we form another set of these subsets. So we say A, B, C, D, right? So now P is called the partition of X. So here A, B, C, D are all non-empty sets, or rather subsets of X. Second is A union B union C union D is equal to X. And pairwise, if you take any of these two subsets, if you take their intersection, it will always be null set. So A intersection B is equal to B intersection C equal to C intersection D equal to A intersection C equal to B intersection D equal to A intersection D is equal to null set. That means they have nothing in common, right? So what basically what it boils down to is you have a set A, B, C, D, right? E, F, and basically what you are doing is based on some criteria you are creating subsets out of them, right? Without any commonalities. So if this is X and let's say this is A and this is B, then another set of these subsets A comma B is the partition of X. You are dividing up the set. Okay, now let's based on this look at a couple of theorems. Theorem 1, an equivalence relation defined in a set decomposes the set into disjoint equivalence classes. So if you think about it, it actually makes sense. You have a set with n number of elements, and what you do is you establish a equivalence relation, right? Automatically you will realize that some of the elements become equivalent and you end up with a set of equivalence classes, right? So that is what this statement means. So let R be an equivalence relation on a set S, and let A belong to S and T be a subset of S containing all those elements which are equivalent to A. Okay, so let A belong to S. Now we have taken up A which belongs to S, and T is a subset of S containing all those elements which are equivalent to A. So all the equivalent elements equivalent to A, we put it as a subset. Okay, so which means T is equal to X, where X belongs to S and X relates to A. So here A belongs to T. Since A relates to A, R is reflexive. X comma Y belongs to T. X relates to A and y relates to a, because they are always equivalent to each other, and equivalence is basically reflexive. Okay. Second, x relates to a and y relates to a implies x relates to a relates to y, basically symmetric. So basically what I have done is taken this and taken its symmetric relation. Now this implies x relates to y, so which means based on transitive property, that means T is an equivalence class. So that is one. Now let Z be another equivalence class. So Z is equal to X, where X belongs to S and X relates to B, where B is not equal to A. So we are supposing this, right? Okay, which implies T is not equivalent to Z. Now, since if an element S is common to T and Z, then what would we have? We would have S relates to A and S relates to B. This implies A relates to S and S relates to B, which implies A relates to B, which implies A and B are equivalent. But this is opposite to our supposition. So we have contrariness. B is not equivalent to A. So therefore, T and Z are disjoint. Okay. Now, the next theorem says if R is an equivalence relation in a non-empty set X, then the quotient set X by R, X modulo R, is a partition of X. Okay. Now let's look at it. Each X belonging to X must belong to some equivalence class, right? So if you pick any element from X, it must belong to one of the equivalence classes. And equivalence classes are pairwise disjoint. That means pairwise intersection is a null set. So if Z belongs to X by R, intersection Y by R, then X relates to Z and Y relates to Y. No, Y relates to Z. Okay, which implies X relates to Z and Z relates to Y, because reflexive, which implies X relates to Y. If we say X relates to Y and the relation is what? Equivalence. That means that X by R and Y by R are identical. That means that identical. That means they belong to the same class. So which implies that two equivalence classes are either disjoint or identical. Either they are equal or they are disjoint. Now, the set of equivalence classes is a partition. Remember, we said P is equal to A, comma B, comma C, where A, B, C represent the subsets containing equivalent elements. So if x comma y belonging to a set of partition, then then that means x relates to y. So let's say xy belong to A means that they are equivalent to each other. That means x relates to y, which implies that partition induces a relation. So why, when you're partitioning it, at that time itself you are basically establishing a relationship. Now if C be a partition on X, then the induced relation is an equivalence relation whose set of equivalence classes is X modulo C. So that is equivalence classes and partitioning of a set. That's it for now. Bye.